in Korea. I was really impressed. So Daniel, take it away.
Okay, will do. Whoops, I accidentally closed my screen. Sorry about that. So I will now reshare. Oh, okay. I think I sorry about this.
No,
actually,
no problem.
I also closed my let me.
No, people are still coming, so.
Yeah, sorry, I closed my PowerPoint presentation entirely by mistake because I thought I was accepting the recording starting. But so let me find that.
You can share the screen again.
Yeah, I will do. All right, so now it should be coming up, and let me just start the slideshow.
That's perfect. Now 50 people coming. Yeah.
All right, so here I am, and I think you should see that.
Yes.
Okay, so thank you, Pencheng, for inviting me, and thank everyone for coming. So I'm going to talk about pseudospin-triplet superconductivity in two superconductors that I think are very interesting: uranium, tellurium-2, and cerium-rhodium-2, arsenic-2. In both these materials, I want to emphasize that we're pairing pseudospin, not spin. And so I'm going to talk a little bit about the role of pseudospin in Cooper pairing. All right, so the talk is outlined as follows. I'm going to begin with pseudospin and Cooper pairing. And then I'm going to talk about cerium-rhodium-2, arsenic-2, where there's a field-induced even to odd parity transition. And then I'll talk a little bit about where this even to odd parity state, or how this odd parity state can be stabilized by non-symmorphic symmetries in this material. And then I'll switch to Weyl superconductivity in uranium tellurium-2. All right, so before I do that, let me just acknowledge my collaborators. And so this is work done with a couple experimental groups, 3 of them in particular, in Dresden on the cerium-rhodium-2, arsenic-2. Here, the main work was done by Shan-Young Kim and Elena Hassinger. And in the context of uranium tellurium-2, here the main work was done by Ian Hayes and D.D. Wei. And here are my theory collaborators throughout this project. Okay, so why these two materials? I've already hinted at it in both of them. It looks like an odd parity superconducting state or pseudospin-triplet state is realized. And as we all know, such states are very often topological. And so these are both likely to be topological superconductors. And the other thing they have in common, which I want to emphasize today, is that the fermions that give rise to superconductivity or originate from sites that don't have inversion symmetry. And so just to illustrate that, here is the uranium tellurium-2. And so these reds, they're the uraniums. And these uraniums in this material, this is an orthorhombic material, the uraniums in this material form a ladder that run along the A-axis, and the rungs of this ladder are along the C-axis. And in between the two uraniums on a single rung sits the inversion center. So this uranium and this uranium are related by inversion symmetry. In the context of cerium-rhodium-2, arsenic-2, this is a tetragonal material. And again, here we have these cerium layers. And what's important here is the cerium, the inversion symmetry does not sit in a cerium layer, but rather sits between the two cerium layers. Just as I've shown here, that this is an inversion symmetry is not so clear from this picture, but if we look down the A-axis, you can see here's one cerium in one layer, here's another cerium in another layer, and the inversion center sits right there, and you can see that this relates all the atoms within the unit cell. All right, so this local inversion symmetry is important because inversion plays a central role in defining pseudospin. All right, and even more generally, I'd like to point out there is this possibility that there is this deeper link between the site symmetry and odd parity superconductivity. So I've already talked about two materials where the relevant fermions come from sites that don't have inversion symmetry, but it turns out for a series of materials related to uranium tellurium-2, so this ferromagnetic superconductors, which are also orthorhombic, in all these materials, the uraniums again do not sit at sites of inversion symmetry. This is also true for uranium platinum-3 and uranium beryllium-13, and all these superconductors are believed to be odd-parity superconductors. Conversely, if we have the uranium or cerium sitting on sites of inversion symmetry, these superconductors, most people believe them to be even-parity superconductors, suggesting there is this link. And in fact, this link is, of course, not made by me, but was actually pointed out by Phil Anderson back in 1985. And this is a paper Piers Coleman shared with me. And so you can see the underlying sentence that says this suggests that odd-parity triplet superconductivity must have at least 2 F shell atoms per unit cell. Okay. All right, so why is inversion important in superconductivity and in pseudospin? Well, let's first go back to making Cooper pairs. And so in general, we pair fermions at momentum K with fermions at momentum K. And to get a weak coupling instability, or to get a superconducting instability more generally, we want these fermions to be both at the same energy. So we need them to be degenerate. And to ensure that they're degenerate, we have two symmetries in 3 dimensions that do this. One is inversion. Inversion takes a state with spin up at momentum K and transfers it to a state with spin up at momentum minus K. Time reversal takes the state with spin up at K, flips the spin to become down at minus K. Okay, so both these symmetries take K to minus K. Then, of course, their product takes a state at K to another state at K, right? And this product is, well, it's a non-unitary symmetry because of the presence of time reversal, and it squares to -1. And we know that when we have a symmetry that squares to -1, then we have associated with that a Kramer's degeneracy, and that Kramer's degeneracy we call pseudospin. And we often think this pseudospin is very much like usual spin, so we can say there's a spin up and spin down at each momentum K. And as we'll go along, in particular, you'll see that in cerium, rhodium to arsenic 2, and there are circumstances where the pseudospin is not at all like spin, and that leads to some interesting physics. All right, and just to show you how pseudospin can be different than spin, here I've shown you again the structure for uranium tellurium-2, and here I put some F orbitals on the uranium sites, and here's the inversion center again. And so now we imagine a spin up on one uranium site, and then we can ask, what is its pseudospin partner? Well, its pseudospin's partner would be a spin down on the other uranium site. And what's important is that these spins are not on the same site. Okay. So now let's just go a little bit further into some introduction into superconductivity more generally. So let's consider pairing pseudospin states. And so we have 2 states at one momentum K, 2 states at another momentum minus K. And we can make 4 types of Cooper pairs by pairing these 2 states with these 2 states. And we describe this pairing through a gap function, which is delta K, and S prime are the spins at K and minus K. So this delta gap function varies as we move around the Fermi surface. And because we're pairing 2 fermions, we have to satisfy a Pauli exclusion principle with respect to this gap function, meaning that if I interchange a fermion here with a fermion here, then my overall gap function must change sign. And so that's characterized in this picture by interchanging the spin of these 2 fermions and also taking K to minus K. Okay, so in the pseudospin basis then, we find that this leads to generically 2 types of gap functions. One is a pseudospin singlet, where in spin space we have up, down, minus, down, up. And that's characterized by what we call a scalar wave function, psi of K. And to satisfy Pauli exclusion, this scalar wave function has to be even parity. And so satisfy psi of minus K equals psi of K. And so we often just mix up these terms, even parity and pseudospin singlet, because in these materials, they represent the same state. Conversely, we can imagine having symmetry in the spin sector. And so here I've written a gap function that has the spin symmetry in the spin sector. So this is down, up, plus up, down, and then there's up, up, and down, down components. And again, to satisfy Pauli exclusion, because we're symmetric in the spin sector, we have to be anti-symmetric in the momentum sector. And so d of minus k equals minus d of k. And that gives us an odd parity pseudospin triplet state. Now you might think the structure of this gap function in terms of this vector d is fairly odd looking, but it turns out this vector d satisfies a nice property that is under spin rotations, it rotates itself as a vector. And so I'll come back to this in a couple slides when I talk about the role of Pauli or Zeeman fields on such a pairing state. Okay, so with time reversal and inversion symmetries, we can make pseudospin singlet, pseudospin triplet states, and they differ by parity. But of course, when we look at superconductors, we know that we get many different types of pairing states. We call them S wave, D wave, etc. And that additional structure is given by the additional symmetries that our systems have. And so here in uranium, tellurium 2 and cerium, rhodium 2, arsenic 2, we're going to be considering two symmetries. Uranium, tellurium 2, we have an orthorhombic symmetry, and in this material, we have a tetragonal symmetry. And so here are some of the symmetry labels for those states. I'll go into more detail into the specific gap functions a little bit later on when I talk about this more. But here, in the context of the cerium, rhodium 2, arsenic 2, there are a couple key superconducting states that play a role. One is what I call this Rashba spin triplet state, which is also often called a helical triplet state, that has this x hat ky minus y hat kx dependence. And we'll see how we can identify such a state in an experiment in just a minute. And then, of course, there's some even parity states, some of which we're familiar with, an S wave state and a D wave state, kx or minus ky star. Okay, so how can we identify experimentally whether we have a singlet or triplet and what kind of triplet state we have? Well, the most common way is we look at the Pauli limiting field. So in particular, if we start with a system that has no Zeeman field applied, then we at each k, we have a pseudospin up and pseudospin down state. And then if we apply a Zeeman field, we typically split these states to give us two different Fermi surfaces, each one polarized in an opposite direction. Now, if we ask the question, how can we say make a spin singlet Cooper pair out of this? So if we want to pair up with down and down with up, we see we can't do that without costing some kinetic energy because we have to pair on one surface and on another. All right, and so what this typically means is that for a spin singlet superconductor, as we apply a field, we send TC down to 0. And so we typically find that spin singlet superconductors are suppressed at a critical Pauli field that's given by the energy associated with magnetic fields is comparable to the gap. Now you can also see, just looking at this picture, that there's really no problem making triplet states. I can pair this state with this state, and that'll give me a spin triplet state, and that should survive the presence of this Pauli field. But also looking a little bit further, we know that we can have triplet states that are up, down, plus down, up, and that state will have a problem making a Cooper pair because, again, the up and the down are on different Fermi surfaces, so that'll again cost kinetic energy. So spin triplet is still possible, but it depends on which particular triplet state. And here's where the D vector notation is very convenient in understanding. It turns out if our D vector is perpendicular to the applied magnetic field, then there's no Pauli suppression. And then we see that the superconducting state has a magnetic field that survives far past the Pauli field. So here's an example. Here I've taken the field to be along the C axis. All right, and I've imagined first a state that might be relevant for uranium, tellurium 2. Well, probably not, but as an example, comes from there. And so here, because the field is along the C axis and the D vector is along the C axis, this inner product is not 0, and we get a rapid suppression of this triplet superconducting state. Conversely, if we have this Rashba superconducting state that I told you about on the previous slide, here D and H do make an inner product of 0 because the field is along the C axis and the two components of the spin triplet are in plane. And so this state will survive to much higher fields than the Pauli field. There will be some eventual limiting, perhaps an orbital effect or some other effects, but the typical Pauli field will sit way down here and this will go way over that. Right, and so this will play a role in the context of the cerium, rhodium 2, arsenic 2. All right, so that's enough background to get us started on looking at what happens in cerium, rhodium 2, arsenic 2. And so let's just begin right away with what's been observed for the critical fields in this material. All right, so here again, I show you the structure of the cerium, rhodium 2, arsenic 2. And so you can see what happens when you apply the field in plane. And so when you apply the field in plane, here's your critical field, here's your T, and you can see that you get something that, well, maybe resembles a Pauli suppression, though the Pauli field sits somewhere down here, and so you get some enhancement over the Pauli fields. But however, if you look at the field applied along the C-axis, then in that case you get something very different. You see this pronounced kink in the critical field, and then you see that the field far surpasses the Pauli field. So the Pauli field is down here now, and you're orders of magnitude higher than that. And in fact, you're at a much higher field than you are for the in-plane fields. And so one thing you see right away is that there's a very strong anisotropy between the fields along the C-axis and fields in plane. And even though I haven't spelt it out yet, there's actually a very large value of the upper critical field for the field along the C-axis divided by TC. Okay, so let's look at this in a little bit more detail. So here's the upper critical field divided by TC, and here's the value for cerium, rhodium 2, arsenic 2, and you can see it's the highest amongst this set of values plotted, and it sits close to this other set of values that I circle, or this other set of materials that I circle in blue. And if you look at these materials that are circled in blue, it turns out these are all superconductors that break inversion symmetry. They all have large critical fields and large anisotropies, but a key feature is that the material has a C4 Phi point group, and this point group allows the Rashba spin-orbit coupling. So just to illustrate that explicitly, if you look at this material in more detail, here's the HT phase diagram. For fields in plane, you get a suppression of the critical field. But for fields along the C-axis, you can see that you survive to very high C-axis fields, all right, resembling what we saw in the cerium, rhodium 2, arsenic 2. And in fact, in this class of materials, this is understood. Because you break inversion symmetry, you no longer have pseudospin, and the single particle spin degeneracy is split. And because of the point group symmetry, because it's still tetragonal, all that's broken here is a mirror symmetry, you're allowed a Rashba spin-orbit coupling. And so this Rashba spin-orbit coupling gives rise typically to this kind of generic response to magnetic fields, provided that the spin-orbit coupling is much, much larger than the gap. All right, so it seems like this material is in some sense resembles these materials, but there's a problem. And that is that cerium, rhodium 2, arsenic 2 has inversion symmetry, and so it's centrosymmetric, not non-centrosymmetric. So this mechanism cannot directly apply. However, we can look in the literature to see if anything has been done that has some of the key features we have in the cerium, rhodium 2, arsenic 2. And so here, as I mentioned before, the cerium sits not at a site of inversion symmetry, but two ceriums are related by inversion. And in a particular layer, or in particular, a single cerium site has a local C4V point group. And in fact, a single layer of this has a C4V symmetry. And so a single layer allows a Rashba spin-orbit coupling. Global inversion relates this layer to this layer here. And in fact, there is a model that had been studied, which has a lot of these features already. And this is a bilayer model that was studied by Yoshida, Siegrist, and Yanase, where they imagined they had two layers. Each layer individually does not preserve inversion symmetry, but there's an inversion symmetry that does relate these. On one layer, you're allowed to have a Rashba spin-orbit coupling. And since the other layer is related by inversion, it has the opposite sign Rashba spin-orbit coupling. And then you allow these layers to be coupled by some C-axis hopping between them. So you have a spin-orbit coupling and a C-axis hopping. And then in principle, you can allow two gap functions, one on one layer and one on another layer. And so if you apply a magnetic field along the C-axis and you look at what happens to the phase diagram for this particular model, you find the following. You find that you get one state at very low fields where these two gaps are equal, and this is like an S-wave superconductor. And that at higher fields, you find you get this transition where you get this delta and this delta have opposite sign. They call this a pair density wave state, but it's right to call it an odd parity state because under inversion, when you swip delta to minus delta, you pick up a minus sign. And that state is stabilized by a high magnetic field. And so to have this work, you need this spin orbit energy scale to be larger than the c-axis hopping. Okay, so when you look at this, you see there is this clear kink in the critical field, much like the experiment seen in cerium, rhodium 2, arsenic 2. But in addition, there's this predicted phase diagram. And so it's worthwhile going back to the experiments to see if this phase boundary is actually seen. Right. And so here are the results from the Dresden group again. So this is the in-plane field data. Here's the c-axis plane data. And they looked carefully to see if there was indeed evidence for a phase transition here. And sure enough, there was. These stars come from AC susceptibility, but it was also seen with magnetization and magnetostriction. And so what you can see if you look at the AC susceptibility here is you see a feature that corresponds to the onset of superconductivity. You see this other clear feature here that corresponds to this phase line down here. And you can track that in a few places. And you see this second feature in all these probes. And so that naturally suggests that perhaps we realize this bilayer model somehow in this bulk material, cerium, rhodium 2, arsenic 2. Okay, so let me turn to that and try to explore that a little bit more. So here's the bilayer model that I pointed out before from Yoshida, Segrist, and Yanase. And we can see how we can map that into an effective model for the bulk cerium, rhodium 2, arsenic 2. So here we can imagine we have these cerium layers, and on each cerium layer we have an opposite spin orbit coupling. They're related by inversion symmetry. So we can again assign a delta 1 and delta 2 to each of these layers, and then we can have a hopping between the layers T. Right? And as I mentioned before, for this phase diagram to be realized, you need this spin orbit coupling to be much larger than the c-axis hopping. And in bilayer materials, you can imagine you can actually engineer this, and that was the motivation for considering this in the first place. Perhaps you can put some some material between these that allow you to reach this limit that the c-axis coupling is smaller than the spin orbit coupling, but it's not as obvious that you can do that in a bulk material like cerium, rhodium 2, arsenic 2, that the spin orbit coupling is going to be larger than the c-axis hopping scale. In fact, if you look at transport data and DFT data, it's not so obvious that this is actually the case. Right? And so we have to ask the question, can this occur in a bulk material? And it turns out, in particular for cerium, rhodium 2, arsenic 2, the surprising answer is yes. And it turns out to be closely linked to the non-symmorphic space group. All right, so let me turn to this in the next slide. Before I turn to that, sorry, let me just tell you a little bit about the superconducting states that we can expect in this cerium, rhodium 2, arsenic 2. So what we've seen with respect to cerium compounds is that in most cerium compounds, when cerium sits on an inversion site, we typically expect an even parity superconductor. So odd parity cerium materials are not as common. And so we imagine that some mechanism that underlies superconductivity should give rise to even parity states. And so a natural thing to consider then is superconducting interactions that are, say, on-site, or in this case, in plane. And as long as these on-site interactions or in-plane interactions are much bigger than superconducting interactions between the planes, then in fact you find you naturally get two types of pairing states. One which I call tau 0, which is a Pauli matrix in this layer space, or tau z, which is a c-axis Pauli matrix in this layer space. Let me just illustrate those states. And so this is a tau 0 state. So here is much like in the bilayer system, the superconducting gap function is the same on both layers. This tau z state just quantifies the fact that the superconducting gap function has opposite sign in the two layers, right? And so this is going to be an even parity state, and we're going to study what happens when it becomes a pseudospin singlet state. This is an odd parity state. It must be a pseudospin triplet, and we're going to be looking at this, what happens when we go to the pseudospin limit. The one thing I want to point out is that provided this condition is true, then both channels will be attractive, and so there is a pairing instability in both of these. And in particular, if the interactions happen to be purely on site, then the attractive interaction for both these states will actually be the same. And so you'll have a similar pairing interaction for the same pairing interaction for this state and for this state here, which can help us to understand how both these states can play a role in understanding superconductivity here. Okay, so now let me turn to how it's possible that we can have this effective c-axis hopping to be less than the spin-orbit coupling. And the answer happens to lie in the band structure. And so here, my colleagues, in particular, Tatsuya Shishidu and Mike Weinert, have carried out a renormalized band structure calculation for this, which follows some techniques pioneered by Zwignagel and co-workers. And what they find when they carry out this renormalized band structure is that the Fermi surface here has pockets near the zone edge. And so if you look at the density of states of these pockets near the zone edge, they carry something like 80% the total density of states. So these are our calculations. Zwignagel has done these calculations independently of us and get the same results in this paper here. All right, and so it's natural to ask, well, what does the pseudospin look like for momenta on the zone edge like this? And the very surprising result that you can prove, and I won't go into the details here, but you can prove that for any pseudospin combination, so any arbitrary linear combination of the two spin up and spin down states in pseudospin language, you can show that the expectation value of the spin operator SZ is 0. All right, and this is actually the key observation that allows us to understand how it is that we can get this spin orbit coupling much larger than the c-axis hopping. In particular, if the expectation value of SZ is 0 on this whole face, that means that these spins cannot couple to a c-axis field. So there's no Zeeman coupling to a c-axis field. Right? And so we can then ask, how does this finding relate to this bilayer model that we considered before? And the way to address that is just to say, well, let's look at the bilayer model, apply a Zeeman field along the c-axis, and see what that Zeeman field along the c-axis becomes when it's expressed in terms of pseudospin. Right? So in the bilayer model, we had this c-axis hopping and we had this spin orbit coupling. And what you find is that the c-axis Zeeman field gets reduced by this factor, the square root of t squared over t squared plus spin orbit coupling squared. And so in the limit as t goes to 0, there is no effect of the c-axis field. And that's exactly the same as having this expectation value of spin equals 0 on the zone edge. And so the conclusion is that on the zone face here, this is equivalent to having t equals 0 in this bilayer model. And so for fermions that sit close to here, the key point is that the spin orbit coupling is going to be parametrically larger than the c-axis coupling. And that explains how we can get something that looks very similar to this bilayer model. Okay, and I'll come back to this in a second. Yeah. Okay, so let me just illustrate how this pans out in a more detailed microscopic model, which I won't really give the details for. But you can write down some effective tight binding model for fermions located on these cerium sites, and you can appeal to some experimental measurements to choose the nature of that tight binding model. And then when you study that, you will get a spin orbit coupling that changes sign on both layers and a hopping between these layers. And so we can define a pseudospin from this effective two-band model, and we can project our pairing interactions into that pseudospin basis to talk about the usual scenario for superconductivity. And when we do that, we look at the even parity state that we had before, and we find that this even parity state just becomes a usual pseudospin singlet state, much like, or in particular here, an S-wave state, like the ones that we're used to. All right, and so this state is Pauli suppressed by a c-axis field. That explains why we see some suppression for this state in the low field phase. So this will be the low field phase that's seen. But it's actually less than we expect because of this renormalization of the c-axis field between the c-axis hopping and the spin orbit coupling. So I should point out that I argued that on the zone face, this term is 0, but away from the zone face, this term is not 0. And if you look at the Fermi surface we showed before, there is some Fermi surface also around gamma. And so we do expect to see some Pauli suppression for this even parity pseudospin singlet state. Conversely, if we now project the odd parity pseudospin triplet state into the pseudospin basis, then we get something that looks very much like this helical triplet or Rashba triplet state I mentioned before. And I see I've put this bracket in the wrong place, but look at the form of the numerator of this term. You can see that this sign kx and the small kx limit becomes like kx. And so this looks like kx sigma y minus ky sigma x. So this is this Rashba triplet state I mentioned before. And if I apply a field along the c-axis, this term is not suppressed at all by a c-axis field. Right? And so this naturally explains how we have one term that's insensitive to field, one state that's insensitive to field, and one state that's sensitive to field. Another thing I would like to point out here too is that the gap magnitude for this state is suppressed by a factor alpha over the square root of t squared plus alpha squared. And so the net gap for the pseudospin triplet is less than the net gap for the pseudospin singlet state. And the physical consequence of that is that this state must then have a lower TC in zero field than this state here. All right, so putting all that together in terms of understanding the experiments. So for in-plane fields, this pseudospin triplet state is suppressed or is Pauli suppressed, and so we don't expect it necessarily to appear. And so for in-plane fields, we see that we get this phase diagram for the even parity state, where the superconducting state survives above the Pauli limiting field and relatively large amount above the Pauli limiting field, because this effective coupling to the c-axis same in field. The effective coupling is changed by the presence of the spin orbit coupling present here. But we can model this well using our theory. And then if we look at the c-axis fields, then we find that in this case here, we have, again, the two superconducting states we identify as an odd parity state in the high field limit and as an even parity state in the low field limit, exploiting the fact that we have this spin orbit coupling that is effectively much larger than the c-axis hopping near these zone boundaries. All right, and so we find a good agreement between theory and experiment. And I think more generally, this points the way to making or stabilizing spin triplet superconducting states by a magnetic field. And so it'd be interesting to look at further examples of that. Okay, so that's what I want to say about cerium, rhodium 2, arsenic 2. And let me now switch to Weyl superconductivity in uranium, tellurium 2. All right, so let me just begin here with the observed critical fields as seen by Zhang and co-workers. And so here, this is an orthorhombic material. And so if you apply the fields in the 3 different directions, you'll get different critical fields. And here you find experimentally that the upper critical field is different in all 3 different directions. So for the field along the A-axis, you get this critical field. For the field along the B-axis, you get this critical field. Sorry, C-axis, you get this critical field. And for the field along the B-axis, you get this critical field that far surpasses the Pauli field. It looks like these 2 fields far surpass the Pauli field. The Pauli field is somewhere around here. And so it's very reasonable to assume this is actually a spin triplet superconductor. There's some night shift measurements that suggest this is indeed a spin triplet superconductor. And so a pseudospin triplet superconductor. And so one question we can ask then, assuming it is spin triplet, is what can we say about the order parameter and what can we say about the quasi-particle excitations in this superconductor? And so those are the 2 questions I'm going to answer in the rest of the talk. Okay, so to answer this, the key experimental result I'm going to refer to is the observation of broken time reversal symmetry by polar Kerr measurements done by D.D. Weyl and Aaron Kapitulnik's group. And so here, what was measured was the Kerr angle as you decrease temperature. And so the Kerr angle is an indication of when you get broken time reversal symmetry. And so if the Kerr angle is 0, time reversal symmetry is preserved. And when it's non-zero, it's broken. And as you see, as you go below the superconducting TC, you go from a signal that's consistent with 0 to a signal that clearly grows below TC. And furthermore, it turns out you can train this signal by applying a c-axis field. So the red dots are for a positive c-axis field, and the blue dots are for a negative c-axis field. And you clearly see that the polar Kerr signal is trainable by a c-axis field. And so we have a polar Kerr effect that is trained by a c-axis field. And this is the key piece of information that I'll use to try to constrain the order parameter symmetries as we go along. There's additional evidence for broken time reversal symmetry, and this comes from Zhao and co-workers in Vidya Madhavan's group, where they have evidence for chiral edge states. And so there's a good amount of evidence that says this superconductor breaks time reversal symmetry, but there's an odd feature of this. In particular, if we want to break time reversal symmetry, we need two components to the superconducting order parameter. And usually this happens when we have some degeneracy. For example, if we have a 3-fold, 4-fold, or 6-fold rotational symmetry, then we often have these two complex degrees of freedom to our superconducting order parameter. But in this material, we don't have that. Rather, we have an orthorhombic symmetry. And so I showed you this table before, and I glossed over the details. And so maybe I'll go into some of the details. Here's the structure just to illustrate that indeed this is orthorhombic. And so here are the pairing states, or the spin triplet pairing states we get for orthorhombic symmetry. And there's 4 of them. And the key point is that these are all described by a single complex degree of freedom, much like an S-wave superconductor. So we have some order parameter psi, and we have one psi for each of these. In practice, when we look at the D vectors for these are some linear combinations of all components of X, Y, Z in the pseudospin triplet basis, and momentum functions Fx, Fy, and Z. And here, these momentum functions, we actually generically don't know what they are. And so here I've tried to write down the most general form consistent with symmetry. And this is going to be important when I talk about some more microscopic properties of this state. And when I do talk about these, I'm going to mean Fx has the same symmetry as Kx, or any function that has like Kx. And so, for example, can be sine Kx. Fy has the same symmetry as Ky, but can be in any arbitrary function that looks like Ky, so for example, sine Ky. And similarly, Fz is something that looks like Kz or can be sine Kz. And then there's this other parameter here that shows up in these expansions called Fu. And that's like the product Kx times Ky times Kz. And these particular dependencies will show up later on. So when Kx equals 0, this Fx equals 0. When Ky equals 0, this equals 0. And similarly, this Fu equals 0, and that'll play a role. All right, but back to the broken time reversal symmetry. We have here all one-dimensional representations. They're all one component order parameters. How can we break time reversal symmetry when we need to have two complex degrees of freedom to do so? Well, the answer was already inherent in measurements by the Grenoble group, where they looked at superconductivity under pressure. And under pressure, what they found is two clear phase transitions, both which they ascribe to be to superconducting phase transitions. And so here you can see one superconducting transition here and another one here. They were unclear what happens as you approach ambient pressure. Do you see two transitions or do you see one transition? But clearly in high pressure, they see two transitions. My collaborators, in particular, Ian Hayes, working in Jean-Pierre Paglione's group, did measurements at ambient pressure. And ambient pressure in 4 different samples shown here, and in fact, in many, many samples they've grown, they see clear evidence for two transitions. And so that's what's shown here. And so you see two clear specific heat anomalies. And so it looks like the answer to how you can get broken time reversal symmetry is that you actually get two superconducting representations that are not degenerate by symmetry, but happen to be accidentally degenerate in a particular regime of pressure and temperature. And so you can get a linear combination D1 plus ID2 that makes your superconducting state in this case here. Okay, so let's try to find out, assume this to be the case, and then try to find out what the Kerr effect tells us about which D1 plus ID2 states are allowed. All right. So as I mentioned before, the Kerr effect is trainable by a C-axis field, and this has implications on the relative symmetry between this D1 and D2. In particular, it means that in our Ginzburg-Landau free energy, we're allowed to write down by symmetry a term that's linear in the C-axis field and couples two of these order parameters where psi1 and psi2 are any one of these four. And the form of this coupling has this form psi1 psi2 star minus psi1 psi2 star, which guarantees that you get a phase factor of I between them when this coupling is non-zero. But you need to have this term allowed by symmetry in your free energy. And so if that's the case, the symmetries of psi1 and psi2 are restricted. And in fact, it turns out there's only two possibilities that allow this term to exist. And either you have an AU plus I B1U state or a B2U plus I B3U state pairing allowed. Okay, so this constraint from the polar Kerr effect that it's trainable by a C-axis field reduces the number of pairing possibilities and only gives us these two pairing possibilities in uranium-tellurium-2. Okay, so now that's what we can say about symmetry. Now let me turn to nodal excitations. And so very early on in this superconductor, it was identified that if you look at thermal conductivity, the behavior of thermal conductivity is more consistent with a point node behavior than it is with a line node behavior. And so here's some thermal conductivity for a couple uranium-tellurium-2 samples. Here's niobium, which is an S-wave superconductor. And so you can see there's a much larger thermal conductivity for uranium-tellurium-2. And here it's compared to uranium-platinum-3, which is believed to have point nodes for particular field orientation that matters for thermal conductivity. And so it's smaller than that, but it seems consistent with all of this. And so the conclusion from the experiment was that there are point nodes in this material. And so it's reasonable to ask, can we have point nodes in this state D1 plus ID2? And it turns out the answer to this is yes. And it turns out because this is a broken time reversal superconducting state, these point nodes must be Weyl nodes, and there'll be topological Weyl nodes. So all Weyl nodes are topological. But a direct implication of that is if you do have Weyl nodes, you'll also have you'll also have surface states that are Fermi arcs, and that can account for the surface states observed by in Vijaya Madhavan's group for this material when time reversal symmetry is broken. Okay, so let's consider how it's possible in a broken inversion superconductor with broken time reversal symmetry to develop these so-called Weyl nodes. And so a while ago, you can calculate, it was done by Segrist and co-workers where the quasi-particle excitation spectrum was calculated for such a pairing state. And it turns out there's two essential parts to this excitation spectrum. There's this epsilon k minus mu squared term, and this is zero when you're sitting on the Fermi surface. But then you get this d squared plus or minus qk, and this qk is known as a non-unitary contribution, or it's non-zero when the superconducting state is non-unitary, and it's given by this d cross complex conjugate of d. And so that's this d1 plus I2, and the complex conjugate is d1 minus IT2. And when that is non-zero, you get this contribution here. But it turns out you can imagine these two parts in the quasi-particle excitation spectrum as giving rise to two gaps, which I'll call delta plus and delta minus. Delta plus squared is d squared plus q. Delta minus squared is d squared minus q. And you can prove that both of these gaps are positive, so you can call them delta plus squared and delta minus squared. So this looks like a contribution from the kinetic energy plus a gap contribution. And so if we're trying to look for nodes, we want to set these energies to zero. And so we want our fermions to sit on the Fermi surface, and we want our gap to vanish. And a particular gap that should vanish then is the one with the minus sign here. And so we can ask, when does this delta minus square vanish, under what conditions can we impose on D1 and D2 for that to happen? All right, so if you just take this form, plug it into here for D squared, you find that delta plus minus squared takes this form here. And of a bit of algebra, you can convince yourself that if the magnitude of D1 and the magnitude of D2 are equal, and you also satisfy that the inner product of D1 and D2 is 0, at some point in K space that sits on the Fermi surface, then you have a Weyl node. And so you can ask, what kind of conditions does this impose on our superconductivity? Or what conditions, or we can ask, does this generically occur? And so you can see that these two conditions, the magnitude of D1 equals D2, imposes some, is a single condition in a three-dimensional space, so that defines a plane in momentum space. Similarly, this inner product vanishes, also defines a plane in momentum space. And those two planes will generally intersect on a line, and that line will intersect a Fermi surface at a point. And so we can see generically, we have enough degrees of freedom here to have Weyl nodes. And so we do expect that they can exist for this particular odd parity broken time reversal set of states. So they can generically exist, but the question is, do they exist in cerium, rhodium 2, arsenic 2? All right, and so let's examine the B2U plus IB3U state in a little bit more detail. And let's try to ask the question, is it possible that we do satisfy D1 equals D2 and the inner product of D1 and D2 on the Fermi surface somewhere? And we have this condition that we don't really know what these functions fx, fy, and fz are, but we do know their symmetry properties. And so to address this, we can use some insights that we get from topological semimetals, where they found that you get Weyl nodes in high symmetry planes. And so let's consider a high symmetry plane. Let's consider in particular the plane kx equals 0. So if kx equals 0, then if you remember, that means my function fx must be 0 and my function fu must be 0. And so let's look at our B2U and B3U states when fx and fu are 0. So I'm just going to cross out all those terms. And what you see as the result is that this B2U state is along the x direction, this B3U state is along the y and z direction. And so we automatically satisfy the condition that D1 dot D2 is 0. And so we're halfway there to guaranteeing these Weyl points. But to get the whole way there, we want to ask, do we also have the condition that the magnitude of D1 equals the magnitude of D2? I'm not going to go through the details of the explanation, but it turns out you can show that generically you do expect this either in the kx equals 0 plane or the ky equals 0 plane. And so the answer is yes. And so what that means is that for this B2U plus IB3U pairing states, we expect to get 4 Weyl points, and the Weyl charges are distributed as follows. And this means then that we'll also have Weyl arc states. And so those surface Fermi arc states can account for the states, the Majorana edge states seen by Madovan and coworkers, and appear to be a fairly generic consequence of this pairing state independent of the detailed form of the gap functions. And you can show the same thing is true with this AU plus I B1U state, but the details are not exactly the same. There you can, so I won't go into that in more detail, but just refer you to the papers for that. Okay. All right. Okay, so that talks about the pairing symmetry and the nature of the quasi-particle interactions. And maybe Pencheng, I should ask, how much time do I have left? Probably not so much, right? A few minutes?
You can talk 10 more minutes.
Oh, okay. Okay. All right. So then I will talk a little bit more about some details of the microscopics that you can have in the context of this uranium tellurium 2. And I'm just going to make 2 points here. Both of these points are actually closely related to the fact that the uranium do not sit at sites of inversion symmetry. All right, and so the first point I want to make is that there have been some DFT studies on the nature of magnetic interactions in uranium tellurium-2. And here is a reference of that. So this is a Beijing group that carried this out. And what they did is they modeled their spin susceptibilities by effective localized spin interactions to see what you can say are the largest localized type spin interactions, meaning I can have an S1.S2 type interaction, and they deduce that from their DFT results. And so here, the main conclusion of this paper was that when you do this, you find that the strongest magnetic interaction is a ferromagnetic interaction between the two inequivalent uranium in a unit cell. And so you can write this interaction as follows. It's ferromagnetic, so it has a coupling constant -J, where J is positive. And then you can, S1 and 2 corresponds to the sites 1 and 2. And then, okay, in practice, it turns out this coupling constant has to be different for the X, Y, and Z directions. But here, for simplicity, I've kept it the same. And so that's this ferromagnetic interaction that you can have, which is the strongest. Of course, there are going to be additional interactions. There will be spin interactions between this site and this site and further sites, etc. But this is the largest one. And so a reasonable thing to consider is, what does this pairing or this spin interaction imply for superconductivity? And one thing I do want to point out is that these further range spin interactions will guarantee that you either get some ferromagnetic or anti-ferromagnetic states, but this just says that the local spins between these two sites are parallel. But we can imagine moving from one unit cell to other unit cell where we flip these up and down and create either anti-ferromagnet in that magnet in that case, or a ferromagnet. Okay, but let's go back to what kind of pairing states this gives rise to. And you can show that quite generally, you'll get 3 odd parity pairing states. And the symmetry of these 3 states are dictated by the nature of this pairing. And it turns out you'll get an A1U, a B2U, or a B3U pairing. And in practice, you'll get linear combinations of all these D vector components as shown here. And in fact, which one wins depends on, depends on 2 things. Which is the strongest of the J's, meaning I can have a JX, JY, and JZ because this is orthorhombic. So the J in this direction, the J for spins in this direction, this direction, this direction can be equivalent. But also what matters is the details of the spin orbit coupling that stem from the fact that we have 2 inequivalent uranium cells here. And on the interplay of these will determine which of these have the highest TC. And in practice, we don't really know very much about that in detail. But we do know that polar Kerr measurements imply that there must be this B3U plus I B2U state. And so that suggests that in this pairing mechanism, we should get these 2 states stabilized. All right, I'm not going to say much more. I wasn't going to describe too much more about the microscopic details that we had in this context, but simply to say that this pairing interaction then naturally gives rise to this B2U plus I B3U states. And then I guess I have a couple minutes left. And so I'll just tell you one last implication that comes from the fact that we have these uraniums, inequivalent uraniums related by inversion symmetry. And that turns out that if you look at the DFT plus U calculations, you find that there's typically a topological band that sits near the chemical potential. And this topological band has a Z2 invariant that is negative. And physically, when we look at the origin of that topological band, it comes from these F-like orbitals on the uranium site and corresponds to a transition between plus type orbital configuration at the gamma point to a plus minus type orbital configuration at the X point. And so that gives you this, this change of inversion character as you go from gamma to X. And we find that this topological band exists for a large range of U, and this was identified by my collaborator Tetsuya Shishidu in this context. Okay, so on that note, let me come to my conclusions. So You can see a typo in my conclusions here, but in both uranium tellurium-2 and cerium rhodium-2 arsenic-2, the F electron site symmetry plays a key role in the superconducting states. In the cerium rhodium-2 arsenic-2, we get this field-induced multi-phase superconducting state, and we argue that that can be attributed to the non-symmorphic structure and Fermi surface that exists near the zone edges. And so then in that case, the C-axis field drives an even to odd parity transition. And when we switch to uranium tellurium-2, here there's two transitions as evidenced by polar Kerr effect and specific heat. And polar Kerr effect suggests two pairing states. And here's my typo. This should be B through U plus IB through U, or an AU plus IB1U state. And then both these states will likely exhibit Weyl points when either Kx is 0 or Ky is 0. And then wrong ferromagnetic interactions and broken time reversal suggests that there's this B through U plus I B2U state that appears in uranium tellurium-2. Okay, thank you.
Yeah, thank you very much. Yeah, Daniel, it's really exciting talk. Yeah. So any questions for him? Yeah, please. So let me read the first question is, oh, he has no microphone. I guess let me see. Let me try to read it. Experiment could find the boundary between superconducting 2 and superconducting 1 along field, but the theory also predict a boundary at 0 field with a decreasing temperature. Can it be found to confirm the theory?
Yeah, so that's a great question. So let me just go back to that. Okay. Right, let me explain that in a little bit more detail because that was a detail I didn't go over. And so I can show you what the, in the wrong way, sorry. Okay, let me just, all right. Okay, this is the right way. Let me just go back to this phase diagram. Okay, so here's the phase diagram seen experimentally. And as you can see, it's very clear that you don't get this transition at 0 field, right? So the transition really happens at finite field between this state and this state. And indeed, I did say that the TC for the even parity and the odd parity state are attractive. But what happens in practice is even though the TC for both are attractive, once you get pairing in the even parity state, what that typically does is that pushes down the TC of the odd parity state. So the TC of the odd parity state in the presence of the even parity state is not the same as the TC of the odd parity state without the even parity state happening. And so in practice, that's exactly what's happening here. And when we carry out the microscopic calculations, we find that indeed, we never get the spin triplet state appearing or the pseudospin triplet state appearing in 0 field, but rather it does appear in finite field. So I think it does, this answers your question.
I see. So I was curious, Daniel. So for cerium rhodium 2 silicon 2, which I'm not quite familiar with. So what is the magnetic spin fluctuation spectra looks like?
I don't think we know. There's some evidence that there might be some quadrupolar order appearing at some transition temperature a little bit above TC. I mean, it doesn't have as large a specific heat anomaly as the superconducting anomaly, but there is some sort of anomaly there. But other than that, I don't think there is enough neutron scattering data to really identify what the pairing interactions are there.
I see. So, what is the ground state cerium looks like? What does the crystal field level say?
Okay, I do have the answer to that.
I mean, is it a doublet or singlet?
So let me show you. So I do have, here's the slide that addresses that actually. So here, okay. So what they see experimentally is if you look at the entropy as a function of temperature, right, then you find that you get this R ln 4 type behavior at higher temperatures, which suggests that you have two doublets that are relevant. And if you do an analysis of the energy splitting between these two doublets, you find it's about a 30K energy split between them. So by the time you get to the superconducting state way down here, you expect to be only one doublet to be important in that case here. So, but you know, there are two close-flying doublets, and so it's conceivable that there can be some kind of quadrupolar interaction that is created by that.
So then it's basically a spin of a half system, right?
Yes, yes, pseudo-spin half, I would call it.
Yeah, pseudo-spin half, sure.
Yeah.
But I mean, has this been confirmed by inelastic neutron scattering that these two excitation levels are? No,
I don't think so. I think it's all confirmed by basically specific heat susceptibility measurements, etc. So that's where they get this information from. And I'm not really even sure of any neutron scattering data on this material yet. So this is, you know, fairly recent. I think it was first discovered last July to be a superconductor, or well, actually a little bit longer than that. And so not a lot has been done experimentally yet on this.
I see. I mean, TC is rather low, right? 270 milli-K. I mean, it's a tough experiment.
It is. Yeah, so these are hard experiments. I agree. And it's great to the Dresden group for doing this and finding
Dan?
this. Yeah.
Yeah. Thanks, Tim. It was a beautiful talk. I want to ask more question about the UTE2 and the Weyl points and possible Fermi arc between them.
Yes.
And you connected that to you know, the STM measurements from Vidya Madhavan. And I assume they're talking about the finite density states remaining in the gapped state. So she doesn't find that inside the gap that the states don't go to zero or even very close to zero. Maybe there's 20% left residual spectral weight. So if it was just these Fermi arcs, I would think integrating over all of K space, that should be a tiny fraction of momentum space. And I wouldn't expect such a large residual of density states in the STM. Can you comment on, is that intuition correct, or am I missing something?
So I agree with you. And I think this residual density of states is a fascinating problem in this material. So let me point out one other experimental result, not just from Vidya's group, but also from Jean-Pierre's group. So he's done specific heat measurements. Yes. And what he typically finds is that in a specific heat, if you extrapolate the C over T and try to do this area entropy conservation, you know,
it's about half of the state.
Exactly. So there is already a large residual density of state seen in specific heat. But more interestingly is when he does transport, he sees no sign of this residual density of state. So the thermal conductivity doesn't show any residual term coming from this density of states, but rather, it looks like a normal point nodal superconductor in that sense. And so it suggests that somehow these states that are playing a role are perhaps localized in some way. And I think the origin of that is very unclear to me, and I think to many people. So it's, I think, a fascinating question for this material.
But could that be because the fact that the uranium is has a dual character? I mean, has localized as well as itinerant, you know?
Yes, it can be, but I mean, it's easy to say. So I agree, it can be that, but I think it's easy to say dual character, but somehow it's not easy to pull out in a theory so readily, I think.
I mean, I think the problem is that the crystal fuel level for uranium in the system is unknown at this point.
Yeah, I agree. I agree with this, but I still think it's a fascinating problem. So, but again, maybe it is exactly related to this dual character issue that's been plaguing us for years in some sense.
Thank you. And any other questions for Daniel?
So I can comment. My name is Fouquet. I don't believe at all that it is proved that there is double transition from specific heat measurement. People in Grenoble, they have tried very seriously to look if they see double transition. But they believe today that it is quite open question.
Yeah. So this is a good.
We don't believe at all the experiment of A. This figure is very serious. We don't believe even it is very fair. So we don't believe, actually, we have a lot of difficulty in Grenoble to see double transition.
So
Okay,
this is,
I mean, this is really an experimental question. I mean, asking you a theorist kind of unfair. But still,
yeah,
can you
but
answer that?
yes, but I've been,
No, but
yeah.
the theoreticians, they use a lot the double transition because they did for their theories. I am not sure it is true today.
So let me just make one comment on that. I mean, I think, so your experiments do show that under pressure, you have two transitions, right? And so really, this is a question of what happens when we go to ambient pressure at this.
Sure.
And so in principle, I guess the two transitions can cross, or perhaps they can become an avoided crossing along these lines. This is all in principle possible. But what I can say is that, so Ian Hayes has looked at many samples and does see two transitions. And I agree that with your group, you don't see two transitions. And I understand that you have gone to the temperature resolution required to look for it. And so I think what may be happening is that sometimes you do indeed get two transitions and sometimes you don't. And it depends on some sort of details we don't understand yet. And so I should say that when I talk about these states, this AU plus IB1U state, or this B2U plus IB3U state, I'm assuming that polar curve will occur all along this phase boundary, even under pressures, which is something that would be interesting to be measured. And so my feeling is it's quite conceivable that you can have two cases where you see two transitions, you don't see two transitions, and it may depend on some of the details. And one of the fascinating questions is, if that is the case, why does that happen?
I must add, I mean, for uranium dichloride, I mean, it's not even completely clear, what is the key differences in the crystallography of these materials, assuming some samples see two transitions and some samples see, one transition. For example, in the samples that, Ron made, I mean, when we looked at, I mean, he did heat capacity as well. On some samples, he reproduces as a double transition. Other samples, he does not.
I see.
I mean, there's some chemistry problem. I think has yet to be sorted out.
I don't believe at all it is only a chemistry problem. But I was involved 3 decades ago in uranium platinum 3. In uranium platinum 3 was very rapidly verified by many people. There is double transition, so it is solved. But in uranium telluride 2, I think it is quite an open question.
Okay.
Yeah.
And then, so it is not the end of.
Oh, John Pierce, you want to make a comment?
Just a quick comment. I know of at least 3 groups, including ourselves, that have synthesized crystals that show the double transition. And in fact, in our group, we've made both kinds of crystals. So some crystals show single transition and some show double. And so I think it is a quote unquote chemistry problem, but I don't know what that means exactly. Whether it's, it's some very subtle variation in the materials properties. But I can say that, starting with the same raw materials, we see both types of crystals. And we very readily see this double transition in many, many samples.
I could agree with Jean-Pierre on this, yeah.
Yeah, I don't think it's a question of whether it's true or not. It's there. And it's just, the question is what's controlling whether it appears or not.
But if you compare to uranium platinum 3, there is no comparison. In uranium platinum 3, the problem was solved in a few months. In uranium telluride 2, actually, it is quite open question. I believe that is quite open question. I don't believe it does not exist. I think the problem is not solved.
Yeah, no, on that I agree. I mean, but I do agree with Jean-Pierre that one probably needs to do a much more detailed characterization in terms of a chemical structure to see whether there are potentially defects. But it's not an easy problem to solve. I mean, to see whether potentially you have a tellurium, defect or something that can control whether it's a double transition or not. I mean, like I was saying, in some of the samples that we have, we do see a double transition. Other samples we only see one transition. It's just like Jean-Pierre was saying. Dan?
Yeah, can I ask, are there correlations, this is to Jean-Pierre, of course, between RRR and whether or not there's 2 correlations or other signals of, purity?
No, so far there's nothing obvious. And I think one important observation, which is sort of a non-observation, but is that whenever you see these double transition, it's not that you see some smeared out thing, the first question would be, is there some distribution of TCs in the sample that's controlled by doping or something like that? And it's never the case that you see something broad and smeared out. There's, whenever you see it, there's essentially two sharp features. And, so what if there was just a distribution of TCs, why would that happen?
I mean, in UPT3, it's believed to be defect, right? I mean, it's believed to be controlled by, stacking, things like that, as Bill Harper was saying.
Yeah, I agree. It could be something very subtle and hard to see in the basic experiments that have been done so far. Time will tell. I don't know. But I think Daniel's point of pointing to the high pressure experiments is very clearly two transitions, and in some phase space of magnetic field and pressure, there's up to 4 distinct superconducting phases. So I don't know how you can think of getting that if it's just coming from stacking faults or something. I just don't. Maybe I'm missing something, but
I mean,
the circumstantial evidence is pretty strong. I think that it's intrinsic.
So maybe I'll make one theory comment on this as well. There is a distinct difference between uranium tellurium-2 and UPT3. In UPT3, to first approximation, most of the superconducting gap functions people study are not non-unitary. And in here, uranium tellurium-2, it seems that we need to have non-unitary gaps to explain the data. And non-unitary states are actually harder to stabilize than the kind seen in uranium platinum-3. And so there could be some energetic reasons for why you have two transitions sometimes and not other times.
Fair enough. Any other question? Okay, if not, I mean, it's a great pleasure to have you giving a talk, Dan. I mean, so thank you so much.
And thank you.
Yeah. Oh, sorry, there's one additional
no,
question
I'm
in the
just
chat.
applauding.
Oh, okay.
You should know that by now, right? There's a difference. Great talk, Dan. Thank you.
Thank you.
Thank you.
All right. Bye, all.
Yeah, bye. Thank you.